Okay, guys, good morning. How's my audio? Can you hear me? Can you guys hear me or not? Okay, somebody text back and say you can hear me. Okay, thank you. All right, so last time we were together, we talked about capacitors. We talked about capacitors hooked up in series and parallel and how they behave. What I want to do now is talk about how capacitors behave in an AC circuit, which, as you'll learn, is quite different than they behave in the DC circuit. So, but to do that, we actually have to review something that you learned in math. We have to have a little trig review, just some basic right triangle stuff. I want to review some basic stuff because it actually has application to what we want to talk about with capacitors, and then you'll see the parallel hopefully before the lecture's over. So we'll start by reviewing some trig stuff, and then hopefully I'll have some time to get into the capacitors. If not, we'll do that in the next video. I didn't get a chance to because I spent a lot of time grading yesterday, but I didn't get to your class, so I need to kind of see where we are work-wise. I know that you guys had exam 2, and I need to get another exam out to you. So I'll look at that in the next day or so, and then I'll probably be pushing something out there before Wednesday. If it's before Wednesday, then I'll send out an announcement on work and just kind of where we are grade-wise because the semester is quickly coming to an end. So let me start this by doing a review on trig, and this is right triangle trig, and everybody knows, I'm sure, that you've seen the relationship when I have a right triangle. They're showing a right triangle by putting this little box here, and these parts of the right triangle, they call those the legs of the triangle. And so, you know, the longest side is the hypotenuse. And the equation that everybody's familiar with is the fact that c squared equals a squared plus b squared. The sum of the square of the legs is equal to the square of the hypotenuse. So, of course, that's Pythagorean theorem. So we actually use this a whole lot in this when we deal with capacitors, and as you'll see when we deal with inductors. But we solve this for C, so we'll actually use it like this. Now I'm going to replace the A and the B and the C with electrical quantities, but it's the same thing. So here's the one you want to familiarize yourself with. So often we'll look for that hypotenuse using this equation right here, so that's important. The angle here is important, theta. Now, you know, if I have a right triangle and I want to find the angle, if I know any two sides, I can find the angle. So any two sides, I can find the angle. The name of these sides, if you don't remember, of course, this is the hypotenuse, the long side. I think everybody knows that. But if I'm here, here's my eyeball, and I'm looking across here, this would be the opposite side. That is, it's opposite this angle. And then the word adjacent means next to. So there's actually two sides that are adjacent to this angle, that are next to the angle, the hypotenuse and then this side A. But since we already named the hypotenuse, we talk about the adjacent side, then we mean this side right here, the adjacent side. So I'm sure everybody's familiar with that. Now the reason I'm putting these on here is because to find that angle, all you gotta know is two sides, any two sides. Well, more often than not, you'll know the opposite side and the adjacent side. And if you remember from your trig, the tangent of the angle is what's equal to the opposite side over the adjacent side. So we use the tangent a lot. We use this formula. So the tangent of this angle right here, the tangent of that angle would equal the way I have it, B over A. But usually we don't want the tangent of the angle, we want the actual angle. So to undo the tangent, you take the arc tangent or the inverse tangent. So if I was looking for theta, the actual angle, theta, then that would be the inverse tangent for that triangle B over A, the inverse tangent. So I would say these formulas here, you've seen them before, I'm sure. Might have been a while since you use them. You use them unless you're taking math now. We use this a whole lot. And again, we'll replace the A, the B, and the C with electrical quantities. The only other thing to know is that if I add up all the angles on the inside, it was a triangle, it's going to add up to 180. I have a 90-degree angle here, so the sum of these two angles will add up to 90, and all three angles add up to 180. The other thing is, if I have a Cartesian coordinate system, which is just a smart person's way of saying the XY axis that you used to work with, and you're measuring an angle. So let's say I have a coordinate system, a set of axes. I can put X and Y on there, it doesn't matter. And let's say I have this arrow here. If I want to measure, there's two ways I can measure. If I measure the angle like this, if I start here and go all the way around, or actually start here and go all the way around like that. So if I'm moving in a counterclockwise direction or anti-clockwise direction, then that's a positive measurement of the angle. And if I measure this way, then that's a negative. I measure a negative angle. So if I measure around this way, I get a bigger number, right? It's almost 360 degrees. So if I measure around this way, I will measure that as a positive. I will record that as positive. If I go the other way, it would be negative. So if I start right here, and I go around and I stop right there, I can write that as that's 270 degrees if I go that way. But if I went the other way to get to the same point, if I start here and I go that way, then I write that as a negative 90 degrees. And they're really the same. If you use, you got the sine, the cosine, the tangent. If you took, let's say, the sine of 270 and the sine of negative 90, you get the same thing, the same answer, because they're the same. I'm pointing this out because usually what we do is we report the smaller angle. So if I go around, even though 270, positive 270 is equal to negative 90, usually I report the smaller angle. So I would write it as a negative 90. It wouldn't be wrong if you wrote the 270, but usually just kind of we use a smaller angle. So really that's all we need for a review. So I can get into some electrical stuff now. If this makes sense to you, which again I'm sure you've seen this many times before. Now we're going to put the electrical spin on it, and we'll replace the A, B, and the C, and the theta and all of that with the electrical quantities. So now we want to look at capacitors in AC circuits. Capacitors in AC circuits. Now let me start by saying AC is a whole different beast. When you start to put capacitors, and I know we haven't talked about inductors yet, but we will. When you put capacitors and inductors in AC circuits, then they behave totally differently than they do in DC circuits. That's not true of resistors though. Let me show you what I'm saying. Let's say I have a DC circuit with a resistor. So I have a voltage source. I got 100 volts DC, and I'm going to hook it up to a resistor That's 1K. And I'm going to connect the same exact circuit with the AC source. So it would look like this. And again, I have 100 volts, 1K ohm. So if I want to find the current in both of the circuits, it's exactly what you think. To find current equals voltage over resistance. This opposition called resistance. And for this circuit, it's just 100 volts over 1K, which gives me 100 milliamps in the DC case. But what if I want to find the current in the AC circuit? Well, it's done exactly the same thing, but remember AC voltage. In AC voltage, there's a lot of different ways to write that voltage. I can write it as a peak voltage. I can write it as a peak to peak. I can write it as an average, RMS, effective. Effective and RMS are the same thing. So you got to be clear what we're dealing with. Now, the way to think about it, at least for this class, anytime you're given an AC voltage, assume it's RMS unless I tell you otherwise. So if I say 100 volts, it's 100 volts RMS. If it was peak or peak to peak, then I would subscript it with a little PK or PP or something like that. So for now, we're always dealing with RMS voltages. So we'll make that clear right now. So that's one thing that's different. What kind of voltage is it? Because whatever kind of voltage it is, if this was a peak voltage, then I would get a peak current when I did the math. If it were peak to peak voltage, I would get a peak to peak current when I did the math. We're going to assume our voltages are RMS, but the process is exactly the same. I'm going to get current. I'm going to take my 100 volt RMS divided by 1K, and just like in the DC case, I'm getting 100 milliamps, but this will be RMS, if this is RMS. So in finding current or doing an analysis in either an AC circuit or DC circuit, it's done the same way. There's no difference in the math. There's no difference in the logic. It's exactly the same. That's not true when I have a capacitor or the inductor when we get to it, or a combination of capacitors, inductors, and resistances. It's different. So I want to talk about the differences, but before I get into that, I have to talk about AC oppositions. In DC, there's only one kind of opposition, and you know it as resistance. Resistance can exist in DC circuits. Resistance can exist in AC circuits. So resistance is opposition to current flow. We're going to talk about other types of opposition to current flow that's not resistance. And the way we talk about resistance, I called it, if you remember, around the second week of class when we were meeting face to face. Wait a minute, did I press the record button? I always forget about that. Yep, okay. I always mess up my videos by not remembering if I pressed the record button or not. But anyway, I forgot what I was saying. Oh boy, I had a senior moment. I don't know what I was saying, but I was talking about the different kind of oppositions. Resistance, what is it? We talked about the billiard ball effect. Remember the billiard ball effect? The fact that if I have, let's say, a copper wire, and that copper wire is composed of copper atoms, and I hook up a voltage source to it, and I try to send a current through that wire, that current is made up of particles, little tiny electrical particles called electrons, and those electrons, as they move through the wire, they collide with the atoms, and they bounce around like a billiard ball. Every time there's a collision, they give up a little bit of energy in the form of heat. And the sum total of all those collisions is what we call resistance. And I call it the billiard ball effect. Well, that billiard ball effect is an opposition to current flow. But as you're going to learn here in just a second, there's other types of opposition. And unfortunately, I don't have time, or it's beyond the scope of this class, to go into the mechanisms of, or the physics behind these other oppositions. All I'm going to do is name them and show you how they apply to an AC circuit. So the thing to remember here is that resistance exists in both AC circuits and DC circuits. Resistance is just resistance. Doesn't matter if it's hooked up to a DC source or an AC source. So I'm going to erase this, and I'm going to write down the various oppositions that you're going to come across and tell you if they're AC opposition or DC opposition. And I'll tell you now, the only one that's both AC and DC is resistance. All right, so I'm going to get rid of my title here. And I'll do it like this. DC and AC. And these are oppositions. All right? Well, in DC, there's only one kind of opposition. We've been dealing with it all semester. That's resistance. And we thought about or think about resistance as the electrical equivalent of friction. The electrical equivalent of friction, and resistance is always associated with heat. That's important. Resistance is always associated with heat. Well, in AC, it turns out that there are several types of opposition. There's resistance. So that billiard ball effect that I talked about can exist in both DC circuits or in AC circuits. But in AC, there's also something called reactance. And that's the new one, reactance. Reactance is the opposition you get when you have a capacitor or an inductor. These are what we call reactive devices. So if I have a capacitor or inductor, I get another type of opposition called reactance. Now, it's another type of opposition because the way the opposition happens here is the billiard ball effect if I have resistance. Either here or here is the billiard ball effect. But reactance adds the opposition through a different physical mechanism. It's not the billiard ball effect. That's the one thing to understand. The other thing is that if these are ideal devices, perfect devices, then there's no heat associated with these. No heat. No heat. Heat is an energy loss. It's an energy loss. One way to think of reactive devices as energy storage devices. A reactive device like a capacitor will store energy, and if I have a perfect device, it'll store energy, and then I can get the energy back out. And I don't have any energy loss at all. Usually when I have energy loss, usually, not always, but usually it's in the form of heat. If I have a perfect reactive device, there's no heat loss. So that's like a spring. I can put energy in by compressing or stretching the spring. If I have a perfect spring, whatever amount of work or energy I put into compressing or stretching it, when I let it go, I get that amount back out. That's the way to think of a reactive device. So in AC, we got reactance and we got resistance. And there's a third one, because I can have a combination of these two. I can have some resistance and some reactance. When I have a mixture, say if I have maybe I have a resistor, well, that's resistance, and I have a capacitor like that in an AC circuit, that's reactance. Well, the two together, we call that impedance. And this is the way to think about it. That's an M, by the way. It's a terrible looking M. Impedance is resistance plus reactance. So I have a mixture of it like this. They don't have to be in series, but just in the same circuit, if I have some R and C, or if I have some R and we use L for inductors, if I have R and L, or if I have R, L, and C, I might have all three. Then I got impedance. So two new ideas here. Reactance is the opposition added to an AC circuit by either having an inductor or capacitor in the circuit. And impedance is the opposition to have reactive devices like resistors and capacitors mixed up with or included with resistors. And in this case, there is heat loss. And the heat loss is going to come from that part of it. So if I had this circuit right there, and these were ideal devices, I would lose heat here. I have heat loss there, but I wouldn't have a heat loss there. Well, that's not a big deal, but it's just interesting to note that. So let me back up and just kind of re-emphasize a couple points. Resistance exists in every circuit. When I say every circuit, you can have DC circuits, you can have AC circuits, you can even have circuits with a combination of DC and AC together. No matter what kind of circuit you have, resistance can exist in either or all types of circuits. Reactance only exists in AC circuits or AC portions of a circuit. So reactance means that when I put a capacitor in there, it's going to oppose current, just like a resistor, but just a different mechanism. It's not the Berry ball effect. So all opposition, no matter which one it is, if it's resistance, reactance, or impedance, all opposition is measured in ohms. You're familiar with ohms for resistors? Well, if I have reactance, it's measured in ohms. If I have impedance, it too is measured in ohms. So all oppositions are measured in ohms. The symbols you're familiar with for resistance, but let me give you the symbols for reactance. So we all know that, let me erase this and I'll just put the symbols up here. So we all know the symbol for a resistor. We use R. We use an R for resistance. Now for reactance, we use the letter X for reactance. So, but now we have two, because remember, reactance can come from, there's two reactive devices. There's the one we talked about already, the capacitor, and there's the one we're going to talk about, the inductor. And so I got to be able to tell which one I have. So if I have X, if I put a C there, that means that those reactive ohms, that opposition is coming from a capacitor. And if I have an inductor, I know you like to put an I there because inductor is spelled with an I, but we use I for current already, so we can't use I. They use an L. So this right here is capacitive reactance, and this one is inductive reactance. Now I'm going to quit talking about inductor reactance because we haven't talked about the inductor yet. That's common. But we have talked about the capacitor, and so I can talk about capacitive reactance, which is actually the subject of this lecture. So I want to focus on R and XC. We'll focus on circuits with those. So let me go back and show you a couple things to get you to think about this the right way. First, let me point out two things. If I have a capacitor in a DC circuit, and I have a capacitor in an AC circuit, these two circuits are going to behave totally differently. In this circuit, as soon as I hook it up, let's say I got 10 volts and 10 volts. When I hook this up, especially since I don't have a resistor in series with it, what's going to happen is that capacitor is going to quickly charge up to 10 volts, and then it's going to stop. It's going to stop charging, the current will stop flowing. It'll just charge up to 10 volts, and it'll hold that 10 volts as long as it's hooked up in the circuit. Matter of fact, if I take it out of the circuit and set it on the table, it'll still hold the 10 volts, and if I have a perfect capacitor, it'll hold it forever. So in the AC circuit, a capacitor will charge up. That's it. I said that. In a DC circuit, the capacitor will charge up. Once it's charged, it's over. That's it. It just holds the charge. In an AC circuit, it's different. In the AC circuit, this actually provides ohms of opposition. So let's say it provides 10 ohms of opposition. 10 ohms. Well, if it was 10 ohms of opposition, then what will happen is I'll have a current flowing in this AC circuit, and that current is going to equal V over, not R, I was about to write R, it's going to be V over XC, where XC is that value right there. It's the capacitive reactance. It's the ohms provided by the capacitor. And just like with a resistor, I use Ohm's law. I would have 10 volts over 10 ohms, and that'll leave me with 1 amp of current flowing in that circuit of AC current. So whereas over here the capacitor charged up, in the AC circuit, that capacitor is going to provide ohms of opposition that we call reactance, and since it's coming from a capacitor, we call it capacitive reactance. So we're talking about today capacitive reactance. Now, that's kind of a strange creature. Again, I really can't go into the mechanism of it, but I do want to talk about a couple things related to capacitive reactance. The first is capacitive reactance is different from resistance in that it depends on the frequency. So for resistance, for all practical purposes, if I want to find resistance of something, if I know the voltage across the circuit or device, and I know the current through the device, I can get the resistance of the device. But with capacitive reactance, XC, to calculate it, you got to know two things. It's 2 pi FC. And you want to write that down if you're taking notes. Where F is, we talked about the frequency. This is the frequency of the AC waveform, and this is the capacitance of the capacitor. Now, the 2, of course, is a constant. Pi is a constant. And usually when you have a circuit, if you have a circuit and you put a capacitor in it, once you put the capacitor in the circuit, it's a constant. So the only variable we have is frequency. It's possible to have an AC circuit. I can have an AC circuit like this, where I have a capacitor hooked up. And if I put an arrow through it, like a DC source, if I have a DC source, it might be 10 volts, it might be 10 volts. But if I put an arrow through it like that, then what I'm trying to indicate to you is that I can change that from maybe 0 to 10 volts. So that's variable. Well, I can have the same thing over here with AC, but with AC, I can vary the voltage, give you more or less peak voltage, or there's no reason why I can't vary the frequency. Now, I don't know which lab you guys are on. I know Russ told me he was going to give you an AC lab. I don't know if he gave it to you yet or not, but if you do or when you do, you'll notice when you can use your meter to make values, to measure values. And by the way, just since I mentioned the meter, I don't want to confuse you, but in lab, when you guys are making AC measurements, there's two ways to do it. You can use a multimeter like the one we use in class, but you can also use oscilloscope, and you'll be introduced to the oscilloscope in the lab. And the oscilloscope has the ability to measure those other values we talked about, peak to peak. But when you use a meter, a multimeter always measures an RMS. So any meter you use, you get an RMS value. So, but what I was saying here is that I can have an adjustment where I adjust the amplitude of the voltage or the frequency. I can have a knob where I change the frequency, the number of cycles per second. And you can see here that if I actually do that, if I adjust the frequency, look at what happens. If I increase the frequency, if I make this bigger, then these ohms of opposition go down. If I make this smaller, these ohms of opposition go up. So the word reactance, I always look at in here as a subword, react. These are ohms of opposition that actually react to frequency. So I can go in, but I can use this equation to get one value for XC, so many ohms, and I can turn the frequency knob and change that to another value. I never have to change the component. I can change the opposition of that by just changing the frequency. That's one big difference between a capacitor and a resistor. In an AC circuit, the ohms of opposition for a capacitor react to the frequency because they're defined by this equation. So if you're keeping notes, I hope you are, just one equation you want to write down. And then there's some, I'm going to give you a second to write it down, but there's some other very, very important thing. I'm running out of time here, but I want to cover one more important thing to kind of tie things together. And then this will be a good point for me to start with on Wednesday. I want to talk about the impedance triangle. Impedance triangle. And I'm not gonna give a explanation of like the why and the where. I'm just gonna give you the information and then you use it. So when you're dealing with AC, these oppositions are related to each other. Remember, there's resistance, there's reactance, and then if you have a combination of the two, there is impedance. Now, in a DC circuit, it's simple. In the DC circuit, let's say I have two resistors. Let's make them both 10 ohms. And I say, all right, what's my total opposition? You're going to say, well, that's easy. They're in series, I just add them up, 10 and 10, 20 ohms, and you would be correct. Well, if I had capacitors in series like this, and this is 10 ohms, and this is 10 ohms, I do exactly the same thing. If I want to find the total capacitive reactance, just like with resistors, you say, all right, XC total is going to be 10 plus 10 is 20, just like my case with resistors. But here's where it's different. Suppose I had this. I have a resistor that's 10 ohms, and I have a capacitor that had 10 ohms of capacitive reactance. You might think that I would add this 10 and this 10 and get 20, but you'd be incorrect. They don't add up like that. That's where the impedance triangle comes into play. So I'm going to give you the impedance triangle, and I'm going to give it to you the wrong way. I'm going to give it to you the wrong way, and then if I have time, I'll explain the right way. But the wrong way is the way I want you to think about it for right now. So when you do problems on the, I don't know if I'll give you any more quizzes, I don't know, but you got to do an exam at some point over this stuff. It's got to be soon because we only got a couple more weeks. This impedance triangle is what you want to work with. So here's the impedance triangle, the wrong way. So it's a right triangle. And the sides, this is resistance on this side. On this side, this is reactance. Now remember, for reactance, there's two kinds. There is capacitive reactance, and there is inductive reactance. And right now, I'm just focusing on this one, right? But this side is reactance. And if you have a combination of the two, this is impedance. Okay? So I'm going to erase these words and just use letters. And I don't think I gave the letter we use to represent impedance, but I'll give it to you in just a second. Now this angle right here, this angle right in here, that's called the impedance angle. And I'm going to use, we usually use Greek symbols for those. I'm going to use theta z for the impedance angle. So this is the impedance angle, theta z. That turns out to be important. So what I want to do is I'm going to erase the words. You have this in your notes and you'll be able to watch the video. But I'm going to just put the letters here and then show you how they're related to each other. So for resistance, of course, we use a R. We use an X for reactance, and since we're talking about capacitive reactance, I'm going to use an XC for now. And I didn't give you the symbol for impedance, but for impedance, we use Z. So, just like before, where we have Pythagorean theorem, I will write Z squared is equal to R squared plus XC squared. And usually we want Z, the impedance. So what I would do is take the square root of both sides, and I end up with Z. I end up with this relationship. So when I want to calculate impedance, if I have resistance and I have reactance, and they're together like in series, that's how I would do it. I would use this. And then this angle right here, that impedance angle, theta Z, remember I told you that we would use the tangent. Usually you know X and R, so that's the opposite and adjacent. So that's a tangent function. I can use a tangent for that. We usually want to know theta Z, so I'm going to use the inverse tangent. So theta Z is the inverse tangent of XC over R. Now I got to do one thing here that's not going to make sense. I may be able to explain it. If not, I'll have to explain it next time. That I'm going to put a negative sign there, right there. Put that negative sign there, and I'll explain that a little later. Why do I have a negative sign there? But I want to show you what I mean here. If you were calculating with this, what would you do? So remember I had the series circuit? If I had a series circuit like this, let's say that this is 3 ohms, and that's 4 ohms. And then I have the same circuit over here, but this time I got, this is R1, and this is R2. This right here might be R, and this is XC. we'll make them the same value. That's 3 and that's 4, right? So here, if I want to find the total, just like I did before in series, I just add them up. That's what you think. It's 3 and 4. The total here is 7 ohms for RT. I cannot do that here because these add up like a right triangle. And when I say that, I mean they add up like this. So if I want to find the total opposition here, the total opposition here is called RT, the total resistance. But since I have resistive ohms and reactive ohms together, I don't call it the total resistance. This is called impedance. Remember, impedance is resistance plus reactance. And so if I want to find the impedance or the total opposition, I cannot just add them up like I did right here. I got to use this. So what I would do, I would say my impedance is equal to R squared. So I got 3 squared plus, now that XC, I'll go ahead and write it as 4, but you really, often I'll put a -4 in there. I'll probably just put that -4 in there, but I don't want you to get confused by that. I want to show you why it's -4. I don't know if I'll have time because I got like 3 minutes. So I may have to pick up with this in the next video. But if I do this though, so I'll get the square root, that's 6, no, that's 9 plus 16, which gives me 25, which gives me 5 ohms. So Z is 5 ohms. But with impedance, there's actually two pieces of information. There's Z, and then there's this theta Z too we got to find. So I don't have my calculator, but if you want to find theta Z, then what you would do is you would first make sure your calculator is in degrees. That's important. Sometimes students make a mistake and they'll have it in radians and get the wrong answer. When you're doing this calculation, you need to be in degrees. And then in here I would put -4, and then here I would put the 3, and that would give me theta Z. Again, I don't have my calculator. You can calculate it. So with impedance, you got to report the magnitude, and then there's an angle. Now I got about 2 minutes left. I could show you why this is the case, and it would be really good to show you that. I can probably show you real quick in that way. So the reason this is negative is because that impedance triangle actually came from something called impedance diagram. So I'm going to run through this real quick. I got like less than 2 minutes. And then I'll come back to it. So this is the impedance diagram. This is the impedance diagram. And this axis right here is resistance. And this is impedance. And on the impedance, well, first on the resistance part, it can go from 0 up to any value of resistor. I can have from 0 ohms up to 1,000,000. But I never read a negative value for resistance. So I never ever have to have any negative values for resistance. And then it turns out for reactance, remember there's XL and XC. Well, this part right here is XL. That's inductive reactance, but what we're talking about is capacitive reactance, which is XC. So these values are always negative. So if I have, the circuit I have was this, and I'll come back to this, I'm running out of time. I think this was, this was 3, and this was 4. So what I would do here is I would go over, I will go over 3 units, 1, 2, 3, put a dot. I will go down 4 units, 1, 2, 3, 4, and put a dot. Now notice that's a negative number. That's why that's a negative number here. And then when I go over 3 and down 4, then what I get is a number that's down here. So that number right there will represent my impedance. But this is the last thing, and then I'll stop. This triangle right here, I'm going to draw it. This triangle is like this. This part right here is the 3. That's this. This part right here is the 4. That's this. That's my R, and that's my XC. So the reason you need that negative sign is because that's negative, and that's important because putting that negative there will make this angle negative. And you can see if I measure from here to here, that's actually a negative theta Z. A negative theta Z. Now I went through that kind of fast, so I'm probably going to go back through that in the next video. I'll review this, and then I'm going to do some more calculations with this. And then we need to talk about XL because I don't know what kind of lab Russ is going to give you. So, guys, this week, look around. I got to get another exam. I know we talked about a couple things since exam 2, so I'm going to look at that material and give you something else out there to work on because I don't want you I don't want to scammering around on the last week trying to do too much work. So I'm going to be looking at the graded work and kind of see where we are and be looking for me to put up something on Blackboard. Probably before Wednesday, but if not, I'll definitely have something to say about it on Wednesday. You guys have any questions for me before we sign off? Okay, and you guys have a great rest of the day. If you have anything you need to talk to me about, please send me a text. And stay safe, and I'll talk to you guys on Wednesday.